Hi, everybody. I'm Brian Norman. I work for JetBrains on the Kotlin compiler, and I'm here to talk to you about writing your third Kotlin compiler plugin. So the first question you might have is, third? Well, this isn't the first time we've talked about compiler plugins at KotlinConf. In fact, back in 2018, Kevin Most showed us how to write our first Kotlin compiler plugin. Now, at the time, it was mostly like project setup, getting everything configured, and then a bunch of JVM bytecode transformations. And we've obviously moved on from that to being very multi-platform. So back in 2020, there was a blog post by yours truly talking about writing your second Kotlin compiler plugin, where we talked about the new backend IR that I believe was in alpha at the time. We talked about testing, some more project setup, and we just kind of explored what that new backend was going to look like. 2 years ago, there was a talk by Misha, also at KotlinConf, about K2 compiler plugins. And while he didn't really show us how to write a compiler plugin, he did show us some of the new architecture that was involved in K2 and the different extensions that were available. The other question you might be asking is, what's a compiler plugin? I'm kind of new to this territory. I don't really know what's going on. Well, a compiler plugin is kind of an extension. Think of Chrome plugins, Chrome extensions. It's an extension on the compiler plugin that can change language semantics. You can change code, you can generate code as it's being compiled. You can also introduce new warnings or new errors that you might want to have restrictions on your program that you're compiling, or just restrict certain behaviors. However, it is very experimental and very unstable. Another thing that you might have heard of is Kotlin symbol processing. You'd be like, well, this sounds very similar to that, and I can generate code with Kotlin symbol processing. But unfortunately, that's about the only thing you can do. You can't change code as it's being compiled with Kotlin symbol processing, or KSP, and you can't, I don't believe, introduce new errors or warnings. It's also generally a little bit slower than a compiler plugin because it has to process the source code itself. The new KSP2 uses the analysis API to do a pre-process on the code, and then compilation kicks in. But it does have a very stable API, and it maintains binary compatibility across versions. So what would my recommendation be here? Well, in fact, I would say if you can use KSP, use KSP. It's stable. You're going to have a much better maintenance story as you upgrade Kotlin. But consider a compiler plugin if you need that deeper integration, if you need to be generating code directly into code that you already have. But also be mindful that as it is an experimental, very unstable API, I'm going to stress unstable again, that there is going to be a significant increase in maintenance cost if you do adopt them. The first-party compiler plugins are kind of exempted from this because they are updated with every new release. And most compiler plugins that you'll see in the community that are popular do maintain their version very well with the compiler as well. So what's possible with a compiler plugin? Well, let's take a look at some examples. So the Spring Boot compiler plugin allows changing the modality of classes that are being compiled. Specifically, we are going to open them so that the proxying that Spring Boot does can take effect on all of your beans. Another really good example here is serialization, which is able to generate a serializer for you that works with JSON, protobuf, and a bunch of other things. It generates a bunch of code directly into your class that you mark with serializable, and it's able to do checks like making sure that all of the types that you're using in your class are also marked with serializable. Obviously, we can't talk about Kotlin and compiler plugins without mentioning Compose. Compose is able to transform functions that you annotate, adding new parameters like a composer and the changed bit mask, rewriting the body of that function to pass those new parameters onto other composable functions, and making your function skippable and adding groups via the slot table. Another compiler plugin that was mentioned during the keynote was DataFrame. And while this isn't an example of the transformations that the compiler plugin is doing, this is an example of it adding new synthetic properties to frames within your transformations such that you get nice statically typed properties of the data itself that you're dealing with. Gone are the days of needing to use a string to access a specific column in your data frame. And of course, I can't talk about compiler plugins without talking about my favorite compiler plugin, and it has nothing to do with the fact that I wrote it. Trust me on that. This is Power-Assert. Power-Assert transforms function calls by extracting different temporary variables of all of the intermediate values that are part of the expression that you're passing to Power-Assert. And it is able to generate a lovely diagram of all of those values. It's awesome. You should try it. So how does this all work? Well, we need to kind of take a step into the architecture of the compiler. And I like to break this down into 5 stages. The first stage that the compiler goes through is the parse stage. This is where we take Kotlin code, the text file, and we convert it into FIR. Now, FIR is a representation of the structure of Kotlin code. It represents things like a function. And so in FIR, we have something like a class that represents an FIR function. And this will have various properties like type parameters, dispatch receiver, an extension receiver. Also might have value parameters or context parameters, has a return value, a body. Like there's a lot of properties here. And an FIR function is not the only thing. We have an FIR declaration, which is an abstract class that FIR function inherits from. We also have FIR class, FIR file, we have FIR element, and a lot of other things in this abstract syntax tree that we use to represent Kotlin code. Once we've finished parsing the code and we understand what the structure of it is, we need to go through and resolve it. Just because we parsed it doesn't mean that we know what every type is referencing or what every function call is actually doing. So we go through a series of phases, a sequence of phases that slowly resolve Kotlin code. Each phase is kind of responsible for a different part of the FIR structure. And that ordering is very important. We need to understand the supertype of a class before we can resolve types within that class, because that supertype might have a nested class, which is now in scope, etc. So if we take an example here of some ASCII random implementation, we don't know anything about any of the types yet. But as we kind of slowly go through the stages, or the phases rather, of FIR resolution, we kind of slowly begin to understand what each type is specifically working with. And the order here is very important again. We need to resolve implicit return values before we can resolve other functions, because that might influence the local type resolution within other functions. So once resolution is done, we are now able to analyze the code. Just because the code was resolved doesn't mean it's correct. So there are a lot of errors that you might get from the compiler, and we know that the most common errors are resolution errors. Don't know what type that is, don't know what function that is, you used the wrong type in the return, etc. But there are also a lot of errors, and in fact, most errors and warnings are reported during the analysis phase after code has already been resolved. If we take a look at this code can be perfectly resolved. We can understand this fully. There are no resolution errors here. However, we know that division by 0 is going to fail at runtime. We know that you can't return a string from a function that declares that the return type is int. String's not a throwable. That doesn't work. It's pointless to assert that this is null, and there's no return statement at the end, right? So just because you can resolve code doesn't mean that it's correct. And we do this as a stage because then we can report all errors and all warnings within your code at one time. And thus completes the front end of the compiler. This is what we call K2. This is the new compiler front end. So when we talk about that, those are kind of the 3 stages that we're talking about. The remaining is the backend. And to get into that, the first stage is transformation. So we have FIR in the front end, or front-end intermediate representation, but in the back end, we have something just called IR. And you might be wondering, well, why do you have these two things? Well, FIR is very much designed to be resolved. It can be in partial states of resolution, and it represents, again, that structure of Kotlin code. Whereas IR, also a tree-based representation, looks very similar to FIR, but it is more about the semantics of Kotlin code. It represents what is the code trying to achieve rather than what does the source code actually look like. We use IR to convert from high-level concepts down into low-level operations. Each of these is also performed in a series of phases. We call them lowerings in the back end. And so if you take this code example, this isn't exactly what we generate in bytecode on the JVM, for example. In fact, we are able to recognize that that with index can be optimized out, and we just use a local variable for iterating. And the for loop is removed, and we use a while loop instead. And in fact, that range doesn't need to be instantiated every single loop. We can just use range checks instead. So all of these optimizations are performed by the backend, and IR is very tailored to be able to do all of this. The last stage, generation, is probably the easiest to understand. This is where we take IR and we convert it into some platform-specific representation. So we can generate JVM bytecode, JavaScript, LLVM IR, WebAssembly, and Caleb. Not too much there, unless you want to dive into the really specific nitty-gritty of each platform. So those are the 5 stages of the compiler that we'll talk about. And a compiler plugin can influence 3 of them. And it does this with a compiler plugin registrar. This is what allows us to register different extensions with the compiler, allows the compiler to ask the compiler plugin what it wants to do. There's 2 things here. There's an FIR extension register, which allows us to influence the resolve and the analyze stages. The IR generation extension allows us to influence the transformation. And there's some boilerplate here we'll need to look at. To get a compiler plugin registrar, we just need to implement that class and override 2 functions. The first one here is supports K2. Yes. The next one is register extensions. Here we'll need to, again, register those 2 extensions that we looked at, FIR extension register and IR generation extension. I know, these words are very wordy. What are we, Spring? No Spring developers. Okay, got it. Got them. For FIR, we have a bunch of different extensions that we actually have. For example, we have FIR Declaration Generation extension. See, I told you they get wordy. We have FIR Status Transformation extension, FIR Super Type Generation extension, and FIR Additional Checkers extension. All of these help us influence either resolve or analyze, and we're going to be taking a look at a few of these. But for the boilerplate here, it looks very similar to what we had for the registrar. We get this configure plugin, and we can register our extensions with a unary plus. This looks a little weird, but this is ultimately just a factory, and it just needs to take some FIR session, and you need to be able to create your extension from that. Most of the time, you'll see this syntax where it's just a unary plus of the constructor method reference. And so that's kind of all of the pieces. That's everything that's kind of involved, all the stages of the compiler, all the different components that we have for extensions. But let's take a look at an actual example, right? It's always best to kind of have a mental model of what we're trying to achieve. And so for this, well, let's imagine some book class. And it has some properties, and it has a default argument, for example. But this isn't very API friendly. If you want to add a new property, you might then need to maintain multiple constructors. And so oftentimes, libraries will look to have a builder that they have attached to their class. And a builder is not anything complicated. It's rather simple, but it might be complicated to implement. Because if you're dealing with nullable types, you might need to have a flag to recognize whether something's actually been initialized or not, and an actual holder for the value. And you need to throw errors at the right time. For the build function itself, you need to also then check all of those flags, grabbing the holder value, maybe dealing with a default parameter as well, null in this example. And you need to do that for all of the different properties. So there's a lot of boilerplate here. That's very straightforward, but kind of complex, and it's very hard to review in a PR if you don't have unit tests. You should have unit tests. So if we could go back to this, I mean, Lombok can do it. Why can't we, right? Let's make a buildable annotation that is able to generate a builder class for us. So we're going to start on this journey in FIR Declaration Generation extension. This is an abstract class that you can implement, and you'll get access to a bunch of different functions that you can override. I want to take a look at two different categories of these. Nested classifier names and get callable names for class is how we're going to tell the compiler about names of things that we are going to generate. There's going to be two stages here. There's going to be names and actually generating the things as well. The compiler looks through the names of things to understand what it can resolve to before actually trying to gain access to the symbol for return type and other things. So it's better for us to have these two things separated. But to understand what we're actually generating, we also need to look at declaration predicates. These are what help us recognize if something is annotated with our buildable annotation. And we have two examples here. We have buildable predicate, which declares something that is annotated with a fully qualified name of buildable. And we have has buildable predicate, which is a has annotated of fully qualified buildable. What do these things actually mean? Let's go back to our book class. So buildable predicate will match things that are directly annotated with buildable. So in this example, it will match declarations like the constructor. Go back. Has buildable predicate matches declarations that have a declaration that is annotated with @buildable. So in this case, it would match the class book. We can register these predicates with the compiler via the register predicates function. And this notifies the compiler that these are annotations that we care about. So it'll cache all of the declarations that it finds with these annotations internally, making sure that our checks are very fast. So to actually tell the compiler that we want to generate something, we can override, again, this nested classifier names. We can get the predicate-based provider from our FIR session, and we can check to see if the class symbol that we're dealing with matches our predicate of has buildable. Is this a class that has a buildable constructor? If it doesn't, we'll return an empty set, but if it does, we'll just return that name of the builder. This lets the compiler know that this extension is trying to generate something called builder that is a classifier. So if we had an example, use of builder here, the builder kind of goes from red to yellow. We haven't actually generated it yet, but we've kind of notified the compiler that we're trying to generate it. So the compiler then, having seen that name, will come back and say, all right, generate that nested class-like declaration. So it'll give us the owner class here, which will be book in our example, the name and context. And we'll just double check that the builder class name is right. This is actually a useless check. The compiler will not call this function unless the extension has said that it is trying to generate something. But if you are trying to generate multiple classifiers with a single extension, this can be useful for switching over them using a when expression. We'll need to find that actual constructor. So to do that, we're going to use something called an FIR scope. We'll take the owner class symbol that we have and get a declared member scope. This is a way of searching for declarations like constructors or nested functions. This is important because different compiler plugins could interact with each other, and so this will potentially ask other compiler plugins if they would like to generate a constructor for this class. We can use our predicate-based provider again to use that buildable predicate to search for our constructor that is annotated with buildable. Once we have that, it's fairly simple to actually generate the class. There's a utility function provided by the compiler for creating nested classes that takes all the parameters, essentially, that are given to you from the generate nested classifier. And all you have to do is return the symbol. Here, visibility is a little interesting because if the constructor is internal, we want to make sure that the builder is also internal so that we're not accidentally overexposing various types. The other interesting thing that I'll mention here is this key that we need to provide. Builder class key is an implementation of generated declaration key. This is a way of telling the compiler that this is a generated declaration. We can save whatever information that we would like to into this implementation. Here we're going to save the owner class symbol and the constructor symbol for future reference. So back to our example, our builder is now green, or gray, I guess. And we now have a builder nested class. But that wasn't all we wanted to generate. Now we need to actually do all the properties and the functions. So this get callable names for class will get called when we potentially want to generate some callables, and we'll check to see if the classifier origin was that same key. So we can then use that key to get the constructor symbol back out. This makes sure that we have a really efficient way of retrieving that constructor symbol. And then from there, we can get all of the value parameters from that constructor, registering their names as names that we want to generate for properties within our builder class. We also want to make sure that we generate our build function name, as well as this special init, which is the name that we have for constructors. This just notifies the compiler that we want to generate a constructor as well. So now all of our other references here are kind of yellow. We've told the compiler that we want to generate something, but we haven't actually done it yet. Generate constructors will get called when it sees that special init. Here we can again retrieve our builder class key just to make sure that we're dealing with the right thing. And then using the create constructor utility function that's provided by the compiler to create a primary constructor. Buildable key here is just a data object. There's nothing special about it, so I excluded it. Now that we've provided the symbol for the constructor, our code turns green. Something very similar for properties. We'll need to, again, extract that builder class key to make sure that we're dealing with the right class. We can then search through the constructor symbol again, finding that right value parameter that we were dealing with that matches the name of the property that we're trying to generate. If we don't find a match, that will be the case when we're dealing with the build function. If we don't have a build property in the constructor, we'll want to return an empty list. From there, creating a member property, again, a utility function provided by the constructor. Here we can set the return type for this property to be the same as the parameter symbol from the constructor. Make sure that this is a var and it doesn't have a backing field. So now all of our properties turn green and we have a bunch of things in our builder. Function is the last thing we need to do. Checking to make sure that that name is correct. And here it is important because generate functions will get called with all the names of the properties as well, because that was one big set. It won't be called with the constructor because of the special name for the constructor, but it is important here to distinguish that we are generating the build function. Again, getting that builder class key and generating a member function using the utilities provided by the compiler. Here we can get the owner class symbol, the book symbol, from that key as well, and construct a type for it for the return type of our function. And now our yellow build function turns green. Now you might be noticing, well, okay, none of these properties, this function, they don't have bodies, right? Are you just excluding that for brevity, or do they just not have bodies? Well, the truth is they don't have bodies. For the front end, when you're generating declarations, we assume that you're going to generate them correctly and that we don't need to actually resolve anything. So we actually allow you to generate the signature of things in FIR and then implement the body in the transformation phase when using IR. The compiler understands this because of the key that we're using when we build these FIR elements. And it assumes that if it gets past the analysis phase, that everything is okay and that you're going to be able to generate everything correctly. So let's go ahead and look briefly at the transformation. Now, there's been a lot of talk in the community about IR generation extension. So we're going to kind of, again, very quickly go over this. IR generation extension allows you to override a single generate function, which gives you all of the code in your compilation unit as an IR module. This is all of the IR files, every class, every function as a big giant tree. And you can create a visitor to navigate over this entire tree and mutate things as you need them. So let's take a look at this buildable IR visitor. We've got 4 functions here that we'll need to override. Visit element, constructor, class, and simple function, kind of for each of the different categories of things that we were dealing with in FIR. It'll be nice to know when we're dealing with something that was generated by our compiler plugin. And so we'll take that buildable key that we had, that we were attaching to all of the properties and constructors and the functions, and add this buildable origin. This will just give us something that we can compare against for the origin of the IR elements. Because a visitor pattern is very recursive, we'll need to make sure that we're recursing through all of the elements that we care about. That's what we'll do in visit element. Here, we only care about declarations, files, and module fragments. We don't really care about navigating into a function body or anything like that, so we're able to skip those. Now, for the constructor, I'm not really going to show you much. We're going to take a look at matching the origin and making sure that it has an empty body. But again, IR has been kind of talked a bit about a lot. And there's a QR code that you may have noticed in the bottom right, and that is a link to the buildable project on GitHub that contains all of the code for the IR backend. There's a lot of code here, and it's really hard to show this on a slide and not go completely cross-eyed. So if you want to look at all of the details of all of this, I would really encourage you to go to that repository. For the class, it's a little bit more interesting because we actually need to mutate the declarations that are part of the class. So we'll match the plugin key to our builder class key, getting all of those declarations and iterating over them to find all of the IR properties. From that, we can generate some backing fields, update our property accessors, and register those 2 fields that we need, the flag and the holder, in a list, and make sure that those get added to the FIR class, or the IR class. And then, of course, recursing through all of those declarations again to make sure that we transform that build function, which is going to look very similar to the constructor. All right, so that was kind of generation. We can now generate FIR, IR, but the problem here is what happens if there's a class that has buildable on 2 constructors, right? That's not a case that we really can support. We don't know which constructor that we need to reference. And so for this, we might want to actually generate a checker, something that can check to make sure that if a class has buildable on 2 different constructors, we want to report an error. For this, we'll need FIR additional checker extension, which is another abstract class that we implement passing through FIR session. You kind of start to see a pattern here with all of these extensions. Here we can override the declarations checker property and make sure that we provide a class checker. There is a checker implementation, or abstract class rather, for every single FIR element. And we iterate through all of the elements in the FIR tree a single time, making sure that we call all of the respective checkers at each point in that navigation. So here we want to create a buildable constructor checker, but it's going to operate on a class because it needs to navigate through all of the constructors of that class and aggregate them. So our implementation here will be FIR class checker. We're going to use the MPP checker kind common. There's some more information on this specific point. It's a little detailed. Check out that QR code again. There's a bunch of links in the README that might be useful if you're wanting to dive deep into some of these things. Buildable class ID is something that we can also generate from our fully qualified name of our buildable. And then we override the check function here, which gives us the FIR class that we need to check, some checker context, which kind of explains maybe we're nested within a class, what the FIR file that we're dealing with is, just kind of gives us some context around this FIR class. And then the diagnostic reporter that we need to report errors with. We'll build up a list of all of the annotations that we find that match buildable. So if we look at an example, it'll find these two constructors, right? Looking through that FIR scope again to process all of the declared constructors, matching each of those buildable constructors. And if the number of annotations is greater than 1, we'll make sure that we report an error on both of them, turning our green code here into red code. Now to actually report the error, we can just give it the source code for the annotation that we want to report the error on and the context that we're dealing with. And then we can give it a custom error that we create, buildable errors here. Buildable multiple constructors is something that we can create within a base diagnostic rendering factory. There's a lot of components here. I know, it's a lot of code. Each error is defined using a property delegation, or you can define one manually. You give it what kind of element that you want to be reporting the error on. And then you can also define within this map what the actual message of that error is going to be. So in our case, we'll just have a nice simple message of buildable cannot be applied to multiple constructors in the same class. You can register this base diagnostic rendering factory with the root diagnostic rendering factory to make sure that all of these errors, oh my goodness, it's so much code. But that's it. We got through it. Obviously, there's a lot of details here. That QR code, again, full implementation of buildable. You can look through all of the FIR generation, IR generation, and it's not the only thing that you can check out. So again, kind of here, there's the repository on GitHub if you want the name in text and not a QR code. There's also a plugin template project that we have. We're hoping to make this a bit more official by moving it into the Kotlin repository. But we've updated it now for 2.120, and we are hoping to kind of keep it more up to date so that you have something that you can build your compiler plugins with. I'll give you just a second if you want to take snapshots of that slide. Again, all of this information is also available at that QR code. Some sample plugins, if you want to look at some other examples. Burst by Cash App is a really great multi-platform parameterized unit test. It deals mostly with IR transformation and some generation, and it has actually some really great internal documentation as well about everything that it's doing and why. If you want to look at a plugin that's maybe generating some API-friendly value classes, you can look at Poco by Drew Hamilton. This is really a great example of, again, some more code transformations, but also some analysis to make sure that the annotations are being applied in the correct way. So there's some checkers there that you could maybe take a look at to get some examples. And if you want to dive into the absolute deep end of FIR plugins, you could take a look at Metro by Zach. This is a compile-time multi-platform dependency injection framework that uses basically every extension point the compiler plugin framework has. So beware, I guess. And then finally, let's talk a little bit about the future. Obviously, the big question is, when is all of this going to be stable? And I have a bit of a pessimistic answer, which is probably never. The API that we have today was designed for the compiler engineers. FIR and IR is meant to help develop the compiler itself. You can use it. We will probably always provide it as a way of extending the compiler plugin functionality, but we will probably never stabilize FIR and IR and all of those extension points. But what we will probably do, and this is what we're going to be starting work on, is provide an actual stable front-end API that you can use. So you can track that at that KT issue. And yes, this will probably be another API that you have to then deal with. So I look forward to seeing you all at some future Kotlin Conf when we talk about writing your 4th Kotlin compiler plugin. And with that, I want to thank you all for coming, and don't forget to vote.